Good morning, ladies and gentlemen. How are you going today? Today we're going to continue looking at applications of second derivatives. This application or this context is not new to us. We've seen this before. It's essentially looking at displacement, speed, and acceleration. Remember, to get from displacement to velocity, you just have to differentiate. And then if you differentiate velocity with respect to time, so differentiating with respect to time on the top gives us from displacement to velocity and from velocity to acceleration. And hence acceleration is just the double derivative of displacement because you differentiate once and you differentiate once more to get the acceleration. On the other hand, to go backwards, you have to integrate. So you just have to integrate with respect to time. So essentially that's what this little box is saying, is that acceleration is the derivative of velocity, which the velocity is a derivative of displacement. So if you differentiate and you differentiate again, you get the second derivative or the double derivative of displacement, gives you acceleration. So let's look at example number 9. It says here an object travels in a straight line so that its displacement from the origin x, so that's a typo, x meters at time t seconds is given by blah. Part A, work out velocity, work out acceleration. Okay, so let x equal displacement. And it's in meters. Let t equals time, and it was in seconds. Let v equal velocity, which is meters per second, and a is acceleration, which is in meters per second squared or meters per second per second. Okay. So what are we told? We're told that the displacement function as a function of time is t e to negative t, where your domain for your time is from 0 to 5 inclusive. So if we want to work out what velocity is, well, velocity is the derivative, the first derivative of displacement. Now, because in our function with respect to time, because our function has t lots of e to negative t, we need to use the product rule because there's a multiply in it. So using product rule, we have let u be your t, so u dash is 1. V will be e to the negative t, so v dash is negative e to negative t. So v of t, which is your derivative, is u v dash plus v u dash, which is t times negative e to negative t plus 1 lot of e to negative t. That's negative t e to negative t plus e to negative t. I can simplify this by pulling out a common factor. So I have 1 minus t outside of e to negative t outside of 1 minus t. So therefore your velocity function is e to negative t 1 minus t meters per second. Now we need to work out acceleration. Acceleration is the derivative of velocity with respect to time. Again, we have a product of two functions, so let's use product rule. So let u be e to negative t, so u dash is negative e to negative t. If v is 1 minus t, then v dash is negative 1. So a acceleration is u v dash plus v u dash. So that's negative e to negative t. uv dash, yes, plus negative e to negative t 1 minus t. So we have essentially we can pull out a common factor of, we can expand it and simplify it it really doesn't matter. E to negative t minus e to negative t plus t e to negative t. So that's t e to negative t minus 2 e to negative t. So I can pull out a common factor of e to negative t minus 2. So therefore acceleration function is e to the negative t outside of t minus 2 meters per second square. So you finish off with units. So all you need to remember is if you differentiate displacement, you get velocity, and then if you differentiate velocity, you get acceleration as a function of time. Part B, calculate the initial speed of the object. So initial means when time equals 0. So initial speed when time equals 0. So v of 0 is just e to the 0 times 1 minus 0, which is 1. So therefore initial speed is 1 meters per second. Part C, when is the object at rest, and work out the position of the object at this time. So object at rest is when the velocity is 0 because it's not moving. So we need to solve for when v equals 0. So 0 equals e to the negative t lots of 1 minus t. So using null factor law, so e to negative t equals 0 or 1 minus t equals 0. So t equals 1 and negative t equals ln of 0, which is not possible. So object is at rest at time equals 1. What is the position at that time? So x at that time of 1 is 1 lots of e to the negative 1. So that's e to negative 1. So that's approximately, using a calculator, 0.368. So sentence conclusion, therefore object is at rest after 1 second, and its position is e to the negative 1 meters, or approximately 0.368 meters to the right of the origin, because we said that right is positive and left is negative. Right of the origin. Part D, work out when the acceleration is positive. So we want a to be bigger than 0. So the acceleration function was e to the negative t, lots of t minus 2 needs to be bigger than 0. Well, the exponential function is always positive for any x value or t value, right? So since e to the negative t is always positive for all t bigger, or t an element in the reals, therefore for the function to be positive we need t minus 2 to be positive, which means t is bigger than 2. So therefore acceleration is positive when t belongs in when, you know what, let's not use belong in. So when t is between 2 and less than equal to 5 seconds. So when what we just solved then is that if t is bigger than 2, then your acceleration is positive. But don't forget, originally they gave us a domain that it has to be less than or equal to 5. So therefore acceleration is positive for time between 2, not inclusive, and less than or equal to 5 inclusive. So the key point to take away from today is, if you differentiate with respect to time once, you get of displacement, you get velocity. If you differentiate this velocity with respect to time once, you get acceleration. So acceleration is the second derivative of displacement with